Hello, this is Jose Coronado, Product Management Director of Creo Manufacturing Extensions, Subtractive and Additive. Today, I'm with Johannes Willkomm, Research Associate at the Chair for Digital Additive Production at RWTH University in Germany. And we will present a very interesting use case on the additive manufacturing space. So first of all, I will just take 1 minute from your time describing the Creo additive manufacturing strategy. From many releases now, we have been working very importantly focused on lightweight designs. The use case that we will present today is, you will see that it's about that, lightweighting designs using generative and lattice modeling. Also, we have been working on self-supporting geometries, enabled biomimicry, enabled interoperability, and all of this fully embedded into the Creo design environment. So about the design to print process in Creo, this is just for me to highlight something that is happening at the moment in many different industries. There is an intertwined schema between the generative and additive and the regular machining, the regular subtractive processes. So generative design can produce directly machinable shapes, or it can produce bionic shapes, etc. And the interesting thing is that all these processes are complementary, and all of these are supported in Creo. So today we will focus on the additive aspects of these processes. So the main portion of this presentation will be done by Johannes. He will describe the demonstrator done between PTC and the Aachen DAP. So take it from here. Johannes, thank you so much for joining us today.
Yeah, thank you so much. So I will go on with my presentation. As Jose said, I'm Johannes Willkomm. I'm from Germany, from the chair of digital additive production at RWTH Aachen University. And there I'm working on the field of design for additive manufacturing. And in cooperation with PTC, we had 2 different projects where we used Creo additive manufacturing. And today I would like to show you how Creo helps me as a designer for AM. I want to use one of the projects we have done with Creo to demonstrate that. But before I come to the project, I first want to introduce our institute, so who we are and what we are doing. And I would like to give some basic informations about the additive manufacturing process for metals. We call that process laser powder bed fusion, and what design for additive manufacturing or design for laser powder bed fusion means to me. And so finally I come to the project. In this case, it's a motorcycle footrest which we designed with Creo additive. So let me start with a brief description of who we are and what we are doing here in Aachen. We are part of RWTH Aachen University, and as I said, we are the chair for digital additive production. We have more than 35 researchers on these fields, and we are operating on both polymer and metal AM systems. Like our guiding idea, or what we think is we think in digital and physical end-to-end processes, which means for additive manufacturing from the material to the final part. So yeah, to sum up, we can say like we're doing research on the whole process chain of AM and processes for metal and polymers. And the best way to show what we exactly do is to present our 4 groups: digital production, advanced process, advanced materials, and digital product. The research fields of these groups are automatization and data processing, for example, like nesting, slicing, or generating support, production and factory planning. So these are 2 examples for the group digital production. The advanced materials and advanced process groups, as the name of these groups says, these 2 groups are related to material and process development. Therefore we have several AM systems. Also for material development, we have access to a powder optimization plant. They are working on tailored material, also multi-material. The 3rd group, where I am related to, the 4th group, where I'm related to, is the group digital product, where we concentrate on the digital process chain of additive manufacturing, which means like using and development design methods like generative design, topology optimization, but also working on process simulation. As I said, the project in this webinar is mainly about designing parts for additive manufacturing. And in today's examples, or in this example I will show you, we use the additive manufacturing process laser powder bed fusion. So first I would like to shortly explain the process and what design for AM of LPBF means. So LPBF is the powder-based process for metals. On the left side here on this slide, you can see the process steps proceed inside this process. And before you can start printing, before the process starts, you have to slice your model you want to print in the layer thickness. Conventional, this layer thickness is between 30 and 60 micrometers. And after that, the actual printing can start. Therefore, 3 steps are passed through. First, the substrate plate is lowered down by the amount of 1 layer thickness. Then powder material is recoated. And in the 3rd step, the part area of 1 layer is melted by the laser power regarding the sliced model or the sliced part you defined first. And these 3 steps are repeated until the final part is produced. Today we have a huge number of different alloys. They have already been developed for production using LPBF. What I also want to show here is, due to this toolless layer-wise manufacturing process, LPBF offers additional design freedom compared to conventional manufacturing methods as casting or milling. And examples for this additional design freedoms are internal spaces, lightweight lattice structures, monolithic designs where several parts from one component are integrated into one part. And here you can see some examples of LPBF parts, like some topology optimized parts, some parts with 2D or 3D lattice structures. And as you can see, like these parts, it's not possible to manufacture these parts with traditional design or with traditional manufacturing methods. But also, here in laser powder bed fusion, there is no complete design freedom. Besides some design restrictions like minimal size of a geometry feature, there is especially the effect of different cooling of each layer during the process, and this results into residual stresses of our parts. And the build-up of this residual stresses I would like to show on this model I show here on the left side. And the rapid heat input and cooling from layer to layer causes shrinkage of each of the different layers at a different time step. And on the left, you can see the effect on the theoretical model where each layer is separated, but in reality the layers are bonded, and this leads to the residual stresses in the part after the process. And for overhanging features, these stresses results in a deformation. And here on the right you can see like a representation of an overhanging feature with these we call it a downskin angle alpha, which kind of describes the overhang angle, and when this overhang angle is below a critical angle, the deformation results in failed build shapes. To avoid this, we can use lattice or support structures to counteract the stresses and to dissipate the heat during the process. After the process, we have to remove these support structures. What we didn't like, but where I come to is like so we have on the one hand the design potentials of laser powder bed fusion, for example internal complex structures, lattice structures, but on the other hand there are big design restrictions, especially support structures which have to be removed after the process. And for me as a designer, I need a tool to efficiently design complex parts and fulfill the design restrictions of laser powder bed fusion. And this is not possible with conventional CAD solutions, especially to create the complex LPF structures. I rely on a generative design software like Creo. So I need a software like Creo to create such complex parts with respect to the design restrictions of laser powder bed fusion. And this I want to show within within the project here. In this project, we choose like a motorcycle, a Honda Fireblade, which you can see here, and there we choose the footrest as a demonstrator. And conventionally, the part is manufactured by injection molding, and we want to use LPBF to increase the function of the footrest by using generative design and lattice structure, which is both integrated into Creo Additive. So here you can see the approach for designing the part. What is a big benefit of Creo Additive manufacturing is that you don't have to leave Creo for the whole digital process chain. So you don't have to leave Creo for data preparation as, for example, materialized software is integrated here. A couple of years ago, that was not the case. For designing a part with integrated lattice structures, from data preparation or from designing to data preparation, you had to go through several softwares where you had to do data transmission, and this also causes data losses in between these steps. So here we have like a benefit that everything is included into one part. So here the example is to redesign a footrest of this motorcycle. So all in all, we did two redesigns of the part, one only with generative design and one with lattice structures implemented in a generative design topology. So if you might have seen in previous sessions, the redesign with generative design is quite simple within Creo. What we use as a basis for lattice structures is such a bionic design you can see here on the left side of our part. A really important step in designing for laser powder fusion is to define the orientation and placement of our part on the build platform, because the design restrictions rely on this this orientation. So we have to do this in a really early stage of our design process. And this is information we can define inside Creo and use inside several design steps. After designing the part, data preparation is also done within one software here. And if you have the build processor of your machine, you can directly generate the data for printing and send those data to the machine. First, I want to go in more detail of how we designed the lattice design part. Lattice structures are always generated on the basis of a solid model, and as I said, we used a generative design model here for creating the lattice structures in our part. First, the design space of the lattice structures is specified. Usually interfaces to surrounding parts and functional surface are not fitted with lattice structures, as you can also see in this example. And as a cell type, we used stochastic Delaunay lattice structures. Up to a cell size of 5 millimeters, we can print these structures with aluminium alloy, which is quite common in LPBF. So I defined this cell size of 5 millimeters here inside Creo. To avoid stress peaks, I would always recommend to use transition zone between the solid material and the lattice structures, which is also very easy to implement here inside Creo. So the density in this area can be adjusted using a gradient. And finally we got the part with the lattice structures. And one point I would like to add here is that we use simplified representation here inside Creo. This representation in designing parts with lattice structures helps me as a designer quite a lot, because it makes the design process here much more efficient, because with this simplified representation you can the file data is reduced a lot, and so the processing times are much shorter. And the good point here is that I can directly print parts from simplified representation inside Creo. The tray assemblies support generation and data preparation. I would like to show on the generative design part. You can see on the left here. The build direction optimization tool is right on Creo part mode. It is available to the design and manufacturing engineer early in the process to evaluate the impact of a design decision in the context of additive manufacturing. So as I said, orientation is quite important regarding the design restrictions, and so I have the benefit to define that in an early state. When the design is ready, you can select which metal printer you are using for this build job, place the 3D model in the tray assembly, also use an optimization tool to optimize the build direction, and generate support structures, which are generated by materialized support generator technology, which is fully integrated here inside Creo. it is typically that you in your organization or one organization spend a long time, a lot of hours defining their parameter settings for material for one printer technology. So your support parameters for the printer you have for the material you use, and when you have defined these settings, those can be saved on a parameter profile to be selected and used to generate the correct support structure. For slicing the part, in this project we created a .cli file, and once the build processor is finished, we can visualize each layer of the print shop. And these files can be used for printing the parts. In our case, we did it on an EBS M290 RWTH system. Here I've brought a short video of the exposure of the of one layer. You can see here the vectors of support structures exposed by the laser. As we used block support, first a wall of the contour of our support, and after that hatches are exposed. Yes, and after manufacturing, so what we get out of the process then, after we removed the part structures and powder, we got the parts, the two parts you can see on the right here. On the left is the conventional casted part, and the two parts on the right are printed by laser powder bed fusion. So of course it's not about printing everything. We know that LPBF is not the most efficient manufacturing process for real serious parts, but I would say it's about to get from an engineering problem to a physical part. And with Creo additive manufacturing, we have the opportunity to do that very efficient. Here you can see that we have an automatic where we can get from roughly defined boundary condition and fixture points to a complex unique parts. And with this example, I would like to thank you for your attention and would give the word back to Jose. Thanks a lot.
Thank you so much, Johannes. It was a very, very good explanation of the demonstrator. So let's continue. I would like to have 1 minute to describe the progression matrix on Creo. Since Creo 3, we have been building functionality related to additive manufacturing in Creo. We started with lattice modeling, different types of lattices. The most advanced stochastic trabecular shapes were done in Creo 8, for instance. My idea to present this table is not to explain one line by line, but to give you a sense of progression and the types of functionalities we have, like the components we integrate from materialized support structures, the additional functionalities that are embedded inside Creo, like Amphion for distortion compensation, that even if it's not a PTC product by itself, is fully integrated into Creo, just to say a couple of things. Now, as just to finalize, my final message to you is, with additive manufacturing in Creo, we are committed to give you all the functionality in one CAD system, from generative, from parametric lattices with multiple representations. That here, the two use cases presented in the demonstrator was going from generative design to solid modeling and printed, and from also a derivative of the generative design results, but now with lattices, simplified lattices, stochastic lattices in top of that to demonstrate that the simplified representation is completely printable. And we did it. That was the objective of one of the objectives of the demonstrator. You can calculate accurate mass properties from all the geometries. We have simulation-driven geometry, process simulation with Amphion. The connectivity, here we explore the connectivity with CLI, using CLI files. But we have other ways to transfer the Creo model to printers, including 3MF, etc., and others. And our goal is always to have a simple and intuitive UI which is familiar to all Creo users. This is the end of the presentation. Thank you so much for your time.